All right, welcome back. Congratulations to those of you who are still standing or sitting with your eyes still open. It's good. All right, so what we're going to do today, we have 3 hours of lecture. We're going to finish up discussion about mechanism construction, which is at the end of the slides, lesson 5. Then we're going to talk about what chemistry really matters for fuel performance. So we'll talk some more about different requirements that a good fuel should meet, sort of hearkening back to the discussion we had in the very first lecture, and some fuel issues that you should be aware of. And then talk about 3 particular bits of chemistry that are very important for fuel performance: NOx chemistry, ignition chemistry, and soot chemistry. So the ignition chemistry will basically be the first batch of lesson 4 slides that you have. The soot chemistry is the lesson 7 slides, pretty much unaltered. But then this whole stuff here is completely rearranged and new, and so I'll be posting the slides afterwards. They don't match up with the slides you have in your printout. All right. So if you remember yesterday, at the very end, I was showing off these beautiful plots with all kinds of agreement between experiment and the model predictions. And it basically looks like you didn't need to take this class because you could just download the software and predict whatever you want. You never have to learn all these details about how you calculate rates or how you build models or anything. It's all solved. The world is great. No reason to study this field. It's completely solved. And so now I'm going to tell you the truth. So this is true. Sometimes we really can predict the kinetics and get answers that are really close to the experiment. So that is true. But the key word here is sometimes. Okay? And now we'll talk about what the issues are that make it not all the time. So a key part of this procedure is we build the models based on estimates of the thermochemistry and of the rate coefficients. So we have to have a way to make good estimates for every single species and every single reaction that's going to be important in our system. If we make a poor estimate, or we're not even aware that a reaction exists, then our model construction procedure is going to be screwed up. And either we're not going to include an important reaction, or we're going to include reactions which are not important. And then our calculation of the fluxes of the concentration field, concentrations versus time, are going to be messed up. And therefore, our selection of which species next is important will also be messed up. And if you have a bad enough estimate and it hits you in a bad way, the whole model construction can give you complete garbage. So this is a critical issue, is about the estimates. And actually, today, I think this is actually the main obstacle. If we try to extend in new kinds of chemistry, is we hit regions where no one has developed good estimates yet, and then the whole thing's stymied. And it's kind of stupid, right? You think that we know how to do estimates since 1974 or something, so what's the problem? But anyway, it is the problem. Then the next problem is, okay, so suppose you have good enough estimates that you can build the reaction structure, the list of what reactions occur, the identification, which ones are likely to be important. If your estimates are good enough to do that, then the next question is all quantitative. It's about, can we calculate all the rate coefficients? Can we calculate all the thermochemical parameters, all the transport parameters? Can we solve the resulting reacting flow problem? It's all about numerics, right? Can we do it? And this is all about how accurate can we do the quantum calculations. We make a bunch of approximations when we do the quantum calculations. Are the approximations valid for the particular molecule or the particular reaction we're working on? And so this is a little better. You could talk to somebody like me or Dr. Klippenstein, and we could tell you, this type of reaction, you'll be able to calculate accurately. This type with current approximations will be screwed up. You can at least identify where things are likely to go bad. But if you happen to be that the one you care about is the one where it goes bad, then you'll say, rats, the current methods don't work for my molecule. Now I'm going to have to develop a new method. And then that might be another 7 years of work for you or something to figure out a new method to do quantum chemistry. So This is a kind of very, it depends on the system. So if you get a system where the quantum chemistry methods work and are not too expensive, it's like, boom, you can just do the whole thing. It looks great. I showed you some nice examples like that. But if you hit one where the quantum chemistry methods don't work, then you'll never be able to get the numbers right with the current methods. You might have to play around with it for a long time, and maybe none of the methods will work. And so you may have to go and invent new methods. And in fact, in the quantum chemistry community, people are doing that. So there are papers about going back to all the old famous problems molecules that don't work and figuring out new methods to try to make them work. And that's like an ongoing effort. So anyway, so if you have problems with either your estimates or your quantum calculations, it's likely you might get poor predictions. And speed. So if you have estimates, almost immediately you can get a rough prediction. Because if the estimates are good, then the model structure will be good right from the beginning. You run the computer, boom, you don't do any quantum chemistry calculations. Just based on the estimates, you can actually make a pretty good estimate of the products. And when that works, it's fantastic. And in a few days, you might have a model that's pretty good. On the other hand, if you want an accurate prediction, then you have to do this whole iterative cycle where you do sensitivity analysis, do high accuracy calculations for the sensitive parameters, rerun the model generation, including the new parameters, do sensitivity analysis again, find out that some other things are also sensitive that you didn't know about, recalculate those as well, and you might have to do that 10, 15 times before you've actually converged and all the sensitive numbers really are high accuracy. And so that might be a project for 6 months. So you don't know when you get into it actually how long it's going to take you to get a good model. Or if you're ever going to, because if you hit problem A, you may never get a good model. So this is unfortunate things. I would say in general, the methods we have right now are really only good for high temperature, above about 600 Kelvin. When you go below 600 Kelvin, as you'll see, usually our precision of the energy calculations is not good enough, and therefore we have very significant errors in everything, all the equilibrium coefficients and also all the rates because of the barrier heights. When you have molecular weight growth happening on, so for example, you form soot, you have to form polycyclic aromatics. It means the molecules are getting bigger and bigger and bigger, and you get more and more and more isomers at each step. And the complexity of the model just blows up. Also, the size of the molecules gets bigger, and pretty soon you hit the limits of what your quantum chemistry programs can handle. And so then you can't even do high accuracy calculations for a lot of your reactions. And so if you hit a system like that, you're in trouble. This is also if you're in polymerization chemistry, you're in trouble. All the estimates currently are based on a 2D representation of the molecules and are completely unaware of 3D effects. And so that's going to be a problem if the 3D effects matter. For small molecules, usually not. But once the molecules get big enough that they can loop back on themselves, they can rearrange, you start getting all kinds of three-dimensional effects. And then there's some specific types of reactions where it's known that they have what's called stereoelectronic effects. So if you get a physical organic chemistry textbook, they'll have a whole chapter of reactions where it's known that a certain alignment of two functional groups has to be just right. And when they're aligned a certain way, you get a certain reaction. And if they're aligned a different way, they get a different reaction. And so then currently RMG would have no idea about that because it's only representing them all as flat. It doesn't allow for alignment. Currently, we're limited mostly to neutral gas phase species. And we can do maybe a little bit of liquid phase. Currently, we don't have the thermochemistry for ions. Now, people know the thermochemistry of ions, so it's just a weakness of RMG that it's not included. But that's a whole aspect that we'd have to be able to do. And currently, we're mostly limited to CHO molecules with some sulfur, silicon, chlorine, nitrogen. But it's really well tested for carbon, hydrogen, oxygen, and not really well tested for any other elements. All right, so that's the limits. So, yeah, question? Yeah.
When we go to a higher temperature, like 600 degrees, we maintain the pressure, or we go to a lower
RMG can handle the whole range of pressures without much difficulty. So any pressure is okay. It's the temperature is the problem, primarily because there's an error in the energetic calculations. And so the Arrhenius factors are screwed up.
For heavy components, when you go to a higher temperature, it will go to decomposition rather than...
Yeah, that's right. So higher temperature is better. In RMG, higher temperature is better because it tends to make things break up from big to small. which simplifies the chemistry. And also it makes your errors in the E's less important because they're always divided by temperature. It's always E like EA over RT. So if you make the temperature really high, it really diminishes the importance of accurate calculation of the energy, and that helps you. So in both ways, higher temperature is better. So RMG at 2,000 Kelvin, RMG is smokingly great. At 1,000 Kelvin, it's still pretty darn good. If you're at 600 Kelvin, it's flip a coin. Sometimes it works, sometimes it doesn't work. At room temperature, never works. So that's the current situation. All right. Okay, so this rate-based selection means that you have to estimate the rate in order to decide what to select. So you have to have a good estimate of the rate. And if you have an error in the rate estimate, it'll change what model is constructed. The whole structure of the model will be different. And so this can lead to, I mean, often it's not such a big deal. It might just, plus or minus one byproduct species, not a big deal. Sometimes you get completely different answers if you change the estimates. And the problem is, well, the rate estimates tend to be good for reactions that humans think are really important. So if humans think that like H abstraction reactions are really important, and so humans have spent a lot of time measuring them, figuring out procedures how to estimate them, we're good. We're really good for H abstractions. Humans don't think that some other types of reactions are that important, and so hardly anybody ever looked into it. Nobody knows what the numbers are. No one's ever calculated them. No one's ever measured them. And the estimates are just put your finger in the air and wave it around. OK, I got a number. Right? And that's just the way it is. So now it all has to do with what the humans think. If the humans are smart and they're correct, then we only need good estimates for the certain reactions. We're OK. But if the humans were wrong, we wouldn't even know, because we're using their stupid estimate. And their stupid estimate, if it's small, means we'll never see the reaction show up as important. And if their stupid estimate says is too high, so the rate is too high, we'll actually see this crazy species showing up over and over in our model, even though it shouldn't, because if it's too high. So it's very important, actually, for that it be in a certain range of closeness to reality. If it's either too low or too high, we're going to have problems in the model construction. Rate is important, but it is not the same as sensitivity. This is a very crucial conceptual point. So just because a reaction is running fast doesn't mean that you'll be sensitive to it, because actually a lot of reactions that are running fast will almost immediately be partially equilibrated, and in which case you'll be completely insensitive to the rate coefficients and only sensitive to the thermo, the equilibrium constant. And so you'll see no sensitivity even though the rate is super high. On the other hand, you have reactions that are slow. It doesn't mean you can delete them from your model, because if you might still be sensitive to it. So in particular, in pre-ignition chemistry, you're really sensitive to anything that makes radicals. Anything that makes radicals is going to make you ignite. Anything that, if you don't make radicals, you won't ignite. But all the reactions that make radicals are really slow, because you're starting from stable molecules and making radicals. Stable molecules are stable. They don't want to react. So of course, the rates are slow. But some of them you're really sensitive to, because they make the radicals. Yeah?
Is the sensitivity the linear thing, meaning that, let's say for parameter, I pick plus minus 5%, and then I pick plus minus 55%. Could it be that by choosing not enough range of sensitivity, I totally miss something?
Yeah. So typically, people always do is the small perturbation sensitivity. It's called linear sensitivity analysis. You assume basically that it's insensitive to how much you vary it. But in reality, it's not true. In reality, sensitivities are typically sigmoidal. So this is like the sensitivity of my observable. And this is defined as d, typically logarithm of the observable, d logarithm, say, of k, or whatever my parameter is. So I make a plot of this versus the logarithm k. And typically, the sensitivity analysis that we do, if you use ChemKin and press, please give me sensitivities, what it does is doing the slope of this curve. So really, the real shape is usually like this. That there's a certain range where you're getting the kind of linear sensitivities, that you make the rate change a little bit, and it makes a big change in the observable. Maybe this shouldn't just be the logarithm. Let's just be this way. Just do this, actually. I think it might be the same for both, but this is just the observable. Here. This is just the algorithm. So when I make the rate very fast, the reaction will be partially equilibrated. It's going to be flat. So the sensitivity will be 0. The slope will be 0. If I make the rate really slow, the reaction is doing nothing. The observable is not going to change when I change this rate, so the slope will be 0. In this middle range, you'll get something that will be more or less linear. So when you do the local sensitivity, depending on what value you guessed that this rate parameter had, you get different values. You get 0 slope, so no sensitivity, high slope, so you have a high sensitivity, 0 slope again, low sensitivity. And so this is versus the true logarithm of k, but unfortunately we're guessing. We guess this value or this value or this value when we're doing our estimates. So you may not be finding the true sensitivity. And if you varied it by a lot, so here you have a nice linear sensitivity, but if you then extrapolated to what would happen if I made the rate 20 times faster, I might see, oh, I think it's going to really improve my yield. It's going to be great. I'll turn the rate way up. It's going to really improve things. And then you're disappointed because all you get is this little tiny change from here to here because it got flat. Does that make sense? Yeah. All right. There's a proof that the RMG's rate-based algorithm procedure converges always. However, very, very seldom I've ever seen a student bring me a model that's actually converged. And the problem is that because of computer limitations, often we can't actually reach reach convergence. And this turns out to be very problematic for like low-T ignition, for example. All right, another very important concept that's true for any model, not just RMG, but any model, is that each model implicitly has a valid range. If you have a model that's good for something, it's not good for that thing at all possible reaction conditions. It's only good for predicting that thing in a certain range of reaction conditions, because no model is perfect. So what you should do when you make a model is stamp on it, certified only for this range of conditions for predicting this type of observable. And then you've checked, and you're confident that it's good for that. But people shouldn't be taking your model and using it to predict some completely different observable at some completely different reaction conditions, because who knows if your model's being any good for that? Most likely not. And that's because the models are always a truncated expression of reality. We only have a few of the possible species in the world. We only have a few of the possible reactions of the world in our model. And if you get to some sufficiently different condition, some other species or reaction is going to become important. And you've left it out of your model. So this is the idea of the valid range. And it's like the definition of how far the conditions could change before an additional species or reaction would be needed to be added to your reaction mechanism. And there's a paper about this if you want chemical engineering science. Unfortunately, today, almost every model I've ever seen does not say it's valid range. So then it's not surprising that people take the models and apply them completely inappropriately. And so when you write your models, after you've taken my class here, I expect that all your models right at the top will say, the valid range of this model is, and you'll say, from 600 to 900 Kelvin, has to be fuel rich, reaction time has to, conversion has to be fuel conversion less than 90%, or whatever. And you say what it is, and then people would know. But unfortunately, people of the previous generation were foolish and didn't write this down. And so currently, if you take some old model of the literature, it's up to you to figure out what the person's valid range is by reading the paper carefully and figure out what they're trying to do. All right. OK, the temperature. So the rates in the KQs scale as exponentials of energetics over RT. And we're calculating the values of these E's, the energies. And they typically can be off by several kcals per mole. So even if you do the best you can, with your best quantum chemistry that you could afford, you might still be off by a kcal per mole. And so even if you did your best, I'm assuming of course you'll do your best since you're trained by the Princeton Combustion Summer School. All you guys always do your best. So you'll get really great numbers and you'll be good within 1 kcal per mole. you're still going to be off by plus or minus 1 kcal over RT. RT at room temperature is 0.6 of a kcal per mole. At like 500 Kelvin, it's maybe 1 kcal per mole. Up at around 1,000 Kelvin, it's like 2 kcals per mole. So at high T, when you're above 1,000 Kelvin, this is okay. If you do work this well and get to 1 kcal per mole, you're good. But if you're at room temperature, this is not okay. You have an exponential of something bigger than 1 as your error. And so you're off by it could be a factor of 5 too low, it could be a factor of 5 too high. Every single number in your model has these exponentials in it. So you have like a random noise of factors of up to factors of 5 been applied everywhere in your model. And then you just have to hope, well, maybe with all that random noise, it still works out somehow, it cancels out, and I still get a good answer. But who knows what you'll get. So if you want to be able to go to lower temperature, we're going to have to be able to figure out how to get more accurate EAs, especially. And predictions are not perfect yet. So I showed you isobutanol, and that's maybe one of the best models there is. And it matches lots and lots of experiments, and even predicts some experiments that were done after the case. It's really great. And if you predict isobutanol ignition delays in air, they're kind of close. You can see the slope of the line is not quite right, but it's kind of close, so you might be okay. So you might be willing to publish that and say it looks okay. But then if you look at the experiment done where you hold the fuel concentration constant and you vary the O2 concentration, then you see that all the model predictions say that there's no dependence on O2. So no matter what O2 concentration you use, you get the same ignition delays in this model. But in experiment, you get pretty different ignition delays. This is a log plots. This is like orders of magnitude changes in the ignition delays depending on the oxygen concentration. And the model completely misses that. So there's something fundamentally wrong with this model, even though for many of the conventional observations, it looks great. And in fact, this is the conventional way to measure ignition delays, is just to put the fuel in air, and it works okay. And it was only when somebody did this oddball experiment where they held the fuel constant and varied the oxygen that then they realized, oh, there's something really fundamentally wrong with this model. And this is not the only model that's like this. Many, many models, if you look at certain observables, they look great. But then you look at some other observable, they're completely wrong. So it's like, you can be lucky that your model happens to predict some observable, even if the model is incorrect fundamentally. All right, so then you look at that and say, well, why is it so bad? So one reason is just the temperature problem we talked about already. But also there's other problems. So at these low temperatures in oxygen, you get addition reactions of oxygen, so you get a molecular weight growth where you get things that are more and more oxidized. So then the model construction process might not be converged. The tolerance might not be tight enough to pick up all these oxygen species. The quantum chemistry gets more expensive, which the practical consequences is that the person who's making the model says, oh man, I'm running out of my CPU budget. Sorry, I can't do any more calculations. And they just calculate a few of the reactions and they give up because the calculations are taking too long. Next one is that the big molecules have more and more floppy modes. So the rigid rotor harmonic oscillator approximation gets worse and worse and worse as the molecules get bigger. Then the quantum chemistry calculations, the ones that we usually use, have an unfortunate problem that they're particularly bad for peroxy species. And this is related to the fact that peroxy and oxy radicals have two electronic states that are very close in energy, particularly near the transition states for these reactions. So the methods are basically assume that there's a big separation in energy between the ground state and the electronically excited state, but if the two of them go close together, some of the approximations in solving the electronic structure program are not correct. And also, we're still learning about reactions. So I'll show you there's a whole bunch of new reactions of peroxy radicals were discovered in the last 5 years. So the RMG didn't know about them, so it didn't include them in the models. And then as you get to lower and lower temperature, you start making liquids, and then you have to worry about all the condensed phase effects as well. Okay, another problem is slowness. So as I told you, my students very seldomly ever show me a model that's actually converged. And that's typically because the students are impatient and they want a model to be done, and they start running it and running it and running it and running it and running it. And eventually they say, come on, okay, you got to be done now. So they just stop the computer and they show it. Or our computers, we have our own cluster. The power supply is not that stable at MIT. You run it for 3 weeks, something's going to go wrong. And the computer's going to crash, and you just stop. Okay, that's what we got. And so, even relatively simple high temperature systems can involve more than 100 kinetically significant species and greater than 500 important reactions. And the number of edge species grows exponentially, sort of combinatorially, as the core gets bigger. And then if you have systems where you have molecular weight growth happening, you can get orders of magnitude more species and reactions, and particularly in the edge, you get a huge number. So we have to compute all of these thermo and rate parameters. But the quantum chemistry calculations are slow and they're difficult, and so we tend not to do them all. If you want to do them all, it takes a really long time. And part of the slowness is actually that they require human intervention. So the humans have to provide initial guesses at the geometries, particularly for the saddle point optimizers. You need to typically provide quite a good initial guess. And that means the human has to be involved. And if a human has to do 1,000 things, because you have 1,000 reactions to calculate, humans get bored. So after the first 37 transition states, the first 37 you're feeling excited. And then your boss says you got to keep going. And you get up to like transition state number 61. And at that point you say, I'm going to take a break. I'm going to go out and play soccer. I'm going to go sailing. I'm going to do something else because I'm really getting tired of just making initial guesses of geometries of transition states all day. And so even if the computer, if you have unlimited CPU time in the computer, it doesn't mean you have unlimited human time to help the computer to find all its saddle points. We've been working on trying to make automated saddle point search, but I would say so far it's not robust. So often we need human assistance, and this is a big problem. And to try to keep the memory under control, what we've invented is a method called pruning, where in addition to estimating which reactions we think are going to be important, we also try to estimate what things are going to be negligible. And as soon as we decide it's definitely going to be negligible, then we erase it to try to save memory. So it's sort of like as you're writing the reaction network and you're making it bigger and bigger, with your other hand you're going through with your eraser and erasing stuff. And that way you can keep the number of reactions on a piece of paper sort of finite. Otherwise, if you just keep drawing them all the time, eventually you're going to fill up the whole paper, right? It's the same thing in the computer memory. You're eventually going to fill the whole computer memory if you just keep on adding reactions. If you want to read about this, this shows how the memory savings. If you don't do this pruning thing, the memory just goes up and up and up and up. But if you do the pruning, you can keep the memory grows much more gradually. 2D versus 3D. So we've recently had a lot of trouble due to fused ring strain. If you have two rings are fused together, it forces some of the bonds and atoms to take up very particular three-dimensional positions, which currently RMG is not aware of. So RMG thinks that things can be rings that physically cannot. They can't make the molecules curl around in the right way to make these fused rings. So we misestimate the strains. Some molecules have a thing called steric crowding, where you have like two bulky groups have to be next to each other, and they can't. So you can't make a bond between them because they like block each other. RMG doesn't know about that either. RMG doesn't know anything about stereoelectronics. You get intramolecular hydrogen bonding. This is particularly important in biofuels. In biofuels, you often have OH groups, like alcohols. If you have more than one polar group in the same molecule, you can get an intramolecular H bond between the OH group and whatever the other polar group is. And so then the molecule, even though you draw it as a straight line molecule, it actually exists as a cycle because it curls up so that you can achieve the hydrogen bond. And these are very peculiar. So at room temperature, it's actually a cycle. But then as you heat it up to burn it, at some point, you get to such a high energy that the hydrogen bond will melt. You'll break apart the hydrogen bond, and then the thing will start flopping around as a linear molecule. So the heat capacity has a really strange behavior at this temperature, the melting point temperature of the hydrogen bond. And the heat capacity has like a drastically changes, and then you get a big change in the entropy. And so then all the equilibrium constants all change. And currently, nobody keeps track of this. So the model just ignores it, and it's wrong. And then a lot of molecules have conformers related to the fact that there's like several different floppy modes, and certain arrangements are more stable than other arrangements. And again, the current procedures for handling that are not very accurate. And all this stuff is very important for polycyclic molecules and also for reactions through cyclic transition states. For example, intramolecular H abstractions, which I'll show you in a minute, are very important for low temperature ignition. Anyway, if these estimates are way off, then the RMG is either going to omit important species or include stupid species. And either way, once RMG has done that, it's very hard for the program to recover and get those species back if they're supposed to be there. All right, so here's the summary. Predictive kinetics would be really great for combustion. And it's now practical to actually make fairly accurate predictions of the thermo and kinetic parameters with maybe 1 kcal per mole errors, something like factors of 3 on the rates. You can automatically build predictive kinetic models for systems that have carbon, hydrogen, nitrogen, oxygen, sulfur, up to about 10 carbons, guided by the Benson type estimation methods. The sensitive numbers can and should be refined using quantum chemistry. Often the model predictions are quantitative at high T. So these are real predictions followed by experimental tests, not fits to a training set. When you read a paper, if you see that the model matches the data, most commonly it's because someone trained the model to match the data. So just beware. And it's an oddball case where you actually have a prediction that someone did a test on it. But with this new capability, you can switch and work in that mode instead. If you want to get new chemistry or go to lower temperatures, people are going to have to do many, many accurate quantum chemistry calculations to provide the parameter values. But I'd say overall, this is definitely looking a lot more promising now than it did to Dirac back in 1929. So we're making some progress. All right, and I have to acknowledge this whole RMG effort and this whole effort of trying to calculate the rates, this has been an effort of like dozens and dozens of people working really hard for like 20 years. I'm particularly appreciative to the students and postdocs at MIT over the last 15 years who really developed the software to build the models. I think at the moment, there's not a single line of software I wrote that's in any of the RMG package. So my name's on it. Maybe I inspired the students. I got the grants that supported them, but the students did all the work to write the software. And then these are particular people who worked in the specific cases I showed you here. All right. So that's the end of the discussion about mechanism construction. So now, what time is it? Now I want to start a kind of different topic, going back to fuel chemistry, issues and requirements. What do we need in a fuel? And this is very related to pollution. So we talk about NOx. It's also relation to things like ignition quality. So we talk all about this kind of stuff. All right, so we talked before about the requirements on any fuel. So the very key thing is it has to have a large energy density. Usually we achieve that by having a fuel that reacts with oxygen, so we don't have to carry the oxidizer with us. And usually we achieve it by dumping the products out into the environment. That way we don't have to carry the products with us. And by doing it that way, we can achieve really high values of energy density. Now, in reality, you could tolerate a somewhat lower value of the energy density. And so people are working on things like trying to capture the CO2 that's emitted and carry it around on the car with you and return it to somebody who wants CO2. I don't know who wants it, but anyway, that'd be a way to avoid emitting to the atmosphere. So you could go somewhat lower, but you can't really go too much lower, or you'd have to reconceptualize how we're going to run our transportation system. All the cars would have to be twice as big or something if they had to have a gigantic tank to keep some low energy density fuel or capture all the products or carry the oxidizer. All those things would require you to carry a lot more mass of fuel with you. And particularly for airplanes, this is very problematic of how you'll be able to carry all that weight. And we usually want to have hot combustion. This implies very high rates. We get the very high rates because we have very high temperature and because we have a lot of radicals. And that makes all the reactions run really fast. That's great for high power density because you can consume a tremendous amount of fuel really quickly and get a very high, in a very small volume, get a huge amount of energy release. And it's very difficult in almost any other way that you'd be able to achieve that kind of power density. And so you want numbers like this. Sort of typical fuels right now are about 45 megajoules per kilogram, but you could go down to about 10. But below 10, you're starting to have a lot of trouble to figure out how you'd run things. And also volumetric. You don't want to make your vehicles too large. So that sort of puts some constraints. And you're going to have spills, and you're going to dump out your products probably, or even if you capture your products, some of them will leak. And so you really have to worry about toxicity because you don't want to have a disaster every time there's a spill. And as I'm going to show you in a second, the scale is huge. Oh, here we go. So the amount of energy that we want to use for, the amount of energy we use in our system is huge, 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 huge system number. You're never going to replace all of the energy that we use. But even to make an impact at all, you need to be talking on the scale of things 10 gigawatts or bigger. So I ran a discussion in my community about energy. And at the end, the lady said, we have a lot of leaves we collect in our community in the fall. And I noticed people just burn them, and it just makes smoke. And we're not capturing that energy, so we should capture that energy. But then you can do a quick calculation. If you raked up all the leaves and you converted them all into fuel, it's enough to like one car or something, right? So scale really matters. So you need to have, there's a lot of people in the world, they want to use a lot of energy. So things that have to be, just even 1 gigawatts is not enough. Even that's, it's a big power plant. It's not even relevant to really worry about. You need things that are all 10 gigawatts or better, higher, which corresponds in fuel to like 10 million tons per day of fuel. So if you have a resource that's less than 10 million tons per day, it's irrelevant. It's like a niche market. If you want to affect the real problem, you have to be the scale of 10 million tons per day or larger. And it's got to be cheap. If you're going to buy 10 million tons of something every day, you can't spend too much. So you need something that's sort of like less than $20 per gigajoule. That's a very limited range of things you can get that are so cheap. So this is a problem. But all the fuels have to reach this. If you make the price too high, people are just not going to buy it. If you make them buy it and say this is the only energy you're allowed to use, you're going to make the economy crash. And we've seen this multiple times where I'll show you next, that when the oil prices got really high, then the economy crashes. Right? So these gray bands are times of worldwide recessions. And you can see there's like a high correlation with every time there's a jump in the price of oil, then the economy crashes. And if you're going to make the prices all go up by a factor of 3 off this plot, basically the whole economy is going to be crashed. So the economy relies on the energy. People, they're used to using energy to heat their houses, to provide electricity, to be able to get around. And they can spend some more money on energy, but not that much more. Maybe a factor of 3 more. More than that, it's like you're getting out of the range of what's possible. And this is just kind of interesting to tell you, just to show how much the prices fluctuate, which is a lot. This is just oil, but you can look at other energy prices. It's a similar kind of thing. And they're really crazy. And then this is just the price. And then there's the taxes and the government policies about how you can use energy. And they fluctuate just as much as the price does, and sometimes correlated and sometimes anti-correlated, any random thing. So this is like a gambler's thing. You just randomly roll the dice and see what price you get or what tax policy you get. And I would say mostly, this is coming from the cumulative contributions of everybody in the world about how much stuff we buy and who we elect to be our government representatives and everything. So somehow we all contribute to this, but it doesn't look like we know what we're doing. That's my feeling. All right, so one thing I just wanted to point out in this plot, if you start at about 2000 and then you go up to about 2012, the price just went from like really pretty low to zooming up, and it just kept going up and up, except for one crazy excursion around the time of the Great Recession. But otherwise, it's basically doing up, 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 up. A lot. So it went from down near $20 a barrel up to like $100 a barrel, so a factor of 5. So why did the price of oil go up by a factor of 5 in one decade, and pretty much continuously? So that's your quiz question. So it went high, and during that time, gasoline consumption was dropping. So the oil price is going higher, even though the actual amount being consumed in the US and the EU is dropping. And the oil production, on the other hand, was going up like crazy. So really great increase in the total oil production in the world. And during that entire time, the oil price was way higher than the cost of production. So what is going on? Why do you think this happened? So talk to each other. I think none of you know the answer yourselves, so maybe you talk to each other, you'll be able to figure this out. Think of what was happening during that time period, 2000 to like 2012. All right, do we have any guesses what might have been happening, why this happened? Yeah?
Demand growth well outpaced supply growth. So you had global economic growth in that time period.
Okay, and then why did the demand growth go up so high? Do you know where was the demand happening? It wasn't happening in the US, it wasn't happening in Europe.
Everywhere else.
Everywhere else, and where particularly?
Fall of communism, global economic growth.
Okay, so Soviet Union actually, consumption went down.
No, but the world in general, the standard of living has been going up quite considerably.
That's right, so yeah, where was it going? Where was the consumption going up? China, right? Yeah, Southeast Asia and China, right? That's so they went from consuming very, very little oil back in the previous century to consuming as much as US or EU, actually even more, I think now. And so there's a tremendous demand growth, and that's why the oil production was going up like crazy, because the price went up. So if you could produce oil, you would try to produce more because there was new customers who wanted to buy it. But they couldn't keep up, so the producers couldn't develop production capacity fast enough to keep up with how fast the demand was growing. So all through that time, it was a great time to be a producer, or because you're always producing and making a gigantic profit the whole time. The new people in China now were a lot wealthier, and so they were able to buy all this oil, and they had plenty of money, so they didn't care, paying a high price for the oil. It was fine. Yeah?
About in the history, in the past, the gold is connected to dollar, but about the 1970s, they break the connection. So, but the oil is traded with dollar. The more dollars, the more expensive the oil is.
Well, definitely the oil price is traded in dollars. Right? Countries like Saudi Arabia just say, here's our price, we set it in dollars.
So because the world is become more and more wealth, and then there will be one more dollar, and one more dollar, the oil is traded with dollar. I think there are some connections between.
There's definitely some connections, right? And then, I don't know if you guys know how the money supply grows. This is very complicated. I'm not an economics professor. Maybe I shouldn't get into this. But basically, if people have confidence that people will be able to pay them money back, then people are willing to extend credit, even there's no dollars available, and just say, because all these people in Shenzhen make these nice factories, they make these nice iPhones, I think somebody's going to buy those iPhones. They're going to pay a lot of money. So I think the guys in Shenzhen are going to have a lot of money. So therefore, I'll lend them the money to build a factory. I'll lend them the money to buy cars and buy gasoline, and then and it works out. And as long as the amount that's lent matches the expectation is met that they really can pay it back, then everybody's happy and the total global money supply grows. Then in the Great Recession, what happened was it went a little too far. People started to lend money to people that actually weren't able to pay it back. And at some point, then the people don't pay it back, and then all of a sudden everybody's like, uh-oh, I was counting on them to pay it back, and then they can't pay their back, and everybody has a disaster. And that's what happened in 2008, 2009, right? But during this time, definitely that was part of what's going on, is that the consumption was definitely growing in Asia like crazy, as more and more consumers had enough money to buy energy on the international market. And part of that was all due to the global economic expansion. The amount of money was more, because everybody was wealthier, right? But then the speculators got too far ahead, and so they bid the price all the way up to this, which was like totally insane. Right, so you can see how it was going up. It was going pretty fast, but they went really wild right in the early 2008. Went all the way up to $140-something a barrel, and at that price, then people started to question: are they really going to have enough money to pay that? And so then they lost their confidence to lend money to other people. So they're like, I don't think they're really going to be able to pay it back. And so then you can see that boom, it would crash, and it went down by like a factor of 5 in like a couple months. As soon as the confidence was gone. Once things start to drop, everybody loses their confidence all at the same time. They're all afraid, grab my wallet. I need to grab all my money. I don't trust anybody anymore. And so that's what happened there.
The shale oil had an effect.
Yeah, so during this time, the reason why they were able to make enough oil to keep up with the demand, a lot of that was the shale oil production improvements. Actually, a lot of production improvements. But part of it was as the price gets higher, there's more incentive for producers to invent more productive ways to get more. You can do more expensive ways of trying to get the oil out if you're going to sell it for a higher price. And then they make more profit. They can reinvest into R&D to have better technology to get more oil. So you can see a lot of innovations. During the 90s, the oil price was super low. There was like no research, no innovation. It was just puttering along. Actually, a few shale guys funded by the US government working about how to frack shale. Nobody cared because you can't make any money. It's only, at $20 a barrel, you can't do the fracking. But then when the price gets above $50 a barrel or something, all of a sudden you say, hey, I can make a lot of money with the fracking. And so then they deploy it like crazy. When the price is up to $100 a barrel, they're like, ooh, I'm making good money. Right? So everybody tries to go to make shale oil at the same time. All right. Now, the fuel price fluctuate a lot. And that's maybe just an economic curiosity. And it's the way Adam Smith has this hidden hand, that because the price is high, then people work harder to produce more. It's the way it's supposed to go. When the price goes low, then people don't work on that, they work on something else. So it's okay. But it turns out that it's very bad for alternative fuels. I mean, one problem is the big fluctuations can cause recessions. That's bad. But another thing is that if you want to change the energy system in any way, alternative fuels or any other way, you're competing against an established technology. We have established technology that's basically fossil fuels that makes energy at a pretty good price. And when the price goes high, you might say, oh, I can deploy my new technology, my competing alternative fuel. But then when the price goes low, you might lose your shirt because you invested in building capacity to produce this alternative fuel, but if the petroleum producers can undercut you, then you go out of business. And this has happened many times. So particularly like in the late 1980s, at that time the oil price was high. In the early 1980s, the oil price was high, and the governments were concerned about shortage of supply. The governments invested a lot of money in R&D. The companies put a lot of money in R&D. They thought, okay, we're going to switch to alternative fuels. And then the price collapsed. And everybody who put any money into that lost everything. Unocal built a whole city out near the Utah-Colorado border. They were going to produce the kind of shale oil there. They had the schools, the libraries, the roads, the houses. And you can go there, it's like ghost town. Nobody lives there because they never turned it on. Because then they calculated, oh, we're going to be losing money from day one running this. And actually, Unocal doesn't even exist anymore. They had to be taken over. They went bankrupt because of the over-investing. Because they counted the price to stay high, and it just didn't stay high. A lot of examples of this. More recently, there were a lot of efforts in biomass, biofuels. There are many startup companies in biofuels. And I think just like this last week, the very last one went bankrupt. So there were like 40 different companies that got started, and all of them have failed because the oil price went too low. So this is a big problem. And what the consequence is that investors know this, and therefore they say, if you're going to do an energy project, I demand a really high rate of return because I'm taking a big risk. I might lose everything I give to you, you may not be able to pay back to me. So I demand you got to give me 20% per year, 30% per year return. So then that makes it really challenging for the inventor. You have to invent a process that's not only economical, it's got to give fantastic profit, or else the investor's never going to give you money. So either you have to be a sweet talker and persuade them to give them money, lie to them, and say you're going to give them great return and get their money, or you have to have a tremendous technology that's going to give you great profits. It's hard to come up with. And things that are less lucrative never ever get built, even though they might actually work fine. But if they're not going to make enough money to overcome the risk, then they don't actually get built. All right, let's talk back to desirable properties. So requirements are price, energy density, scale. If you don't have any of those things, you don't have a fuel. The desirable properties, you still have a fuel with these things, but they're all desirable. So you'd really prefer to avoid having to deal with solids and powder handling. And currently, mostly in the world, we only do this at very large installations that have very specialized equipment, the big pulverized coal plants. We do it. But everywhere else, we basically try to avoid having to deal with it because it's like a whole bunch of extra headaches to deal with the solids and powders. And so because of this, as we talked about before, this limits you to certain elements that aren't going to make solid oxides products. You really prefer liquid fuels. They have a higher energy density. They're easy to transport. They're easy to handle. They're easy to store. They don't leak because they're not under pressure like gases would be. And they pour. It's a lot easier than solids. And because of this, everybody agrees these are definitely the most convenient, and therefore that's why they're the most expensive. If you pay more for the convenience. You have to make it feasible to control the emissions of health-harming pollutants. And this turns out to be easiest if the fuel evaporates in a certain temperature range, because you want to make the fuel evaporate before it pyrolyzes. So if you have light fuel like gasoline, you heat it up, it evaporates before it does any chemical reactions. So basically, the gaseous fuel is the same molecules that were liquid fuel. On the other hand, if you take something like sugar syrup and you heat it up, the sugar pyrolyzes, it reacts, and changes into a different molecule before it makes any gas. So sugar is no good as a fuel, because you get the pyrolysis chemistry first before you get the evaporation. And so then you typically will always make soot, or make solids, because you're getting pyrolysis and not getting your molecules into the gas phase. And then what you'll have is like little chunks of carbon stuff, and then you're trying to burn a solid again. That's not what you want. And then you'd really like to have minimal or zero greenhouse gas emissions and minimal other environmental impacts. Now, you're going to do something on the scale of tens of millions of tons per day, you're going to have environmental impacts. So it's not like you're going to have zero, but you really want to keep it minimized, because we have plenty of environmental problems in the world already, and you don't want to be contributing even more to the problems in the world. In practice, the emission requirements are really critical, and they really constrain how you can operate the combustion devices. So in gasoline engines, we also call them SI, spark-ignited or auto engines, the fuel-air ratio is held very close to stoichiometric only because it facilitates the catalyst, the exhaust catalyst. There's a thing called the three-way catalyst in the tailpipe of modern cars, and it gets rid of the NOx and the CO. And so that's a really valuable catalyst. And that catalyst is the most important thing, because that allows you to operate without poisoning everybody. And because of that, then you'll just change all the rest of the way you run the opposite rest of the engine just to satisfy the demands of the catalyst. If you don't have a three-way catalyst, and therefore the precise air-to-fuel mixture ratio control you need to work with a three-way catalyst, it's very difficult to meet NOx standards. And so, for example, in the United States, we have a NOx standard. Basically, almost the whole country is violating the NOx standard right now, because all of the other burners besides the cars can't meet it because they don't have three-way catalyst. So, the heater in your house, the water heater, the heater for Princeton Central electric facility and heating facility, the chemical plant down the road where they make, everything is violating the law because they just can't figure out how to meet the NOx standards. And basically what's going to have to happen is they're going to have to go back to all of the existing burners in the whole United States, rip out the existing burners and put in new low NOx burners, or else add emission control devices in the smokestacks. And both of those are going to be very expensive. And so because of that, everybody has been resisting. So the EPA said, that's the rule. We need to have this much NOx. They calculated how much in order to make the air quality standards. And then everybody said, oh my goodness, it means I'm going to have to change my house. And I really don't want to, I don't want to spend $5,000 to change my burner in my house. So I'll just keep quiet about it and pretend. Hope that the government doesn't come after me. And then, right now the government's going after the bigger polluters. So they're going, like in Houston, there's like 10 million chemical and oil companies next to each other. And so they're going after them and saying, you guys have big smokestacks, you're putting a lot of NOx out. Let's get you guys first. And so gradually they're making them go through and rip out the existing burners and put in all new facilities. And they calculate it's like many billions of dollars it's going to cost just in Houston to meet the standards. And all the other cities have the same kind of problem. Now, diesel engines, if they want to try to get the NOx under control, you have kind of two choices. You could try to run diesel with a three-way catalyst. And that's usually called like gasoline compression ignition. And that's a possibility. Or you could try to run in a very special way to keep the temperature very low. And that will minimize the NOx formation. Or you can put an emission system where you react urea with the NOx in the tailpipe. And actually, modern trucks in the US, to meet the standards, most of them have decided to do this. So they mostly you have to separately buy urea, carry it in your truck, and you have to inject it with a special control to match how much NOx emissions you have to make the reaction of urea and NOx to get rid of the NOx. That adds actually, so in a modern truck, the emission control system costs approximately as much as the engine. So it's like you double the cost of the powertrain. But that's how you can make it. And usually you also need a soot filter to get rid of the particulates. So this is quite a contraption. Now, many diesel manufacturers around the world did not want to do this because they said, why should I double the cost of my product to the consumer? It doesn't give them any more. The consumer won't see the benefit. The truck buyer, they still have a truck. But now they have to pay twice as much for the engine. So they were not too happy. So the truck companies were afraid no one's going to buy my truck. And especially the diesel car companies were really afraid because who's going to spend double? The diesel cars are already more expensive than the gasoline cars. And now all of a sudden you have to add another $3,000, $5,000 to the price of a diesel car. It's like, who's going to spend the money? So they didn't want to do it. So instead, they cheated the test. And you guys probably heard about it. It was originally called the Volkswagen Scandal. But now it's turning out that a whole bunch of the other companies did the same thing. And so now there's like 10 billion lawsuits, and you'll be hearing about it in the press for a long time. I don't know, maybe some people go to jail. So they just figured out ways to cheat the test. Another way to cheat the test in some countries is you just slip a bribe to the guy who's doing the test. And he says, oh, great. Right? And so you go to a country and you say, you know, this country's laws say that its air should be beautiful. And then I go outside and I can barely breathe. And say, what is going on here, right? Somehow something's not working. The regulations are written perfectly. You know, they're the same in this country as they are in, you know, United States. But when I go outside in Los Angeles, I can breathe. And when I go outside in the cities in this country, I'm in trouble. And so this is a big current problem that I think is going to happen in all the countries of the world as they try to deal with this. All right, here's a quiz question for you. Last one before the break. The diesel engines are significantly more efficient, fuel efficient, than the gasoline engines. But they're also more expensive to manufacture, and particularly if you want to include the modern emission control systems, it makes it a lot more expensive. Yet, many Europeans buy diesel cars, but very few Americans ever buy a diesel car. So why is that? Why do I think it's even a majority of the European cars, or about 50-50, of the European cars are diesel cars, but in the United States, almost zero. And just to keep in mind that both the emission standards and the fuel prices are very different in Europe than they are in the United States. All right, so talk to your neighbor, see if you can figure out why is this. Why do Europeans use diesels and Americans don't? All right, does anybody have an idea? Why do Europeans get diesel cars and Americans buy gasoline cars? Mileage per liter. Okay, so why do Europeans want to have the higher mileage per liter, but the Americans don't care? So you think it's cultural? It's just people in Europe are more environmentally minded? Let's go. Prices. What's the prices? Yeah, so the fuel prices are much higher in Europe than they are in the U.S. Does anybody have an idea? So in the U.S., the gasoline prices right now are maybe $2.50 a gallon, $2 a gallon. Anybody have an idea of how much the price is in Europe? How much?
I mean, the conversion is kind of weird, but it might be the double. Twice as much, yes.
1.5 euro per liter? 1.5 euro per liter, and a liter is 1/4 of a gallon. So it's something over $6 a gallon in Europe. So in US, the fuel price is actually negligible compared to the price of the vehicle. So you know, the prices are so low. But in Europe, the prices are high enough that actually it's a significant cost of your total cost of transportation is actually the cost of the fuel. And so then it really makes economic sense to pay the extra money for the more efficient engine so you can save on fuel savings. So it's not only that you're culturally environmentally minded, it's good for your pocketbook too, to be environmentally minded. How about the emission standards? Does anybody know about the emission standards difference between US and Europe? Yeah?
I'm not quite sure, but was saying that in Europe, the car company has, so the average of all the car that they are producing, the emission should be less than some amount. But in America, each car, the emission has to be less than the specified amount.
Okay, so that's right. So the testing, the rule about the testing, and actually how the testing is done, they're both really different, and in a way that could lead the Europeans to do a certain thing. But it's also just the standard. Anybody know the standard difference?
Aren't Europeans taxed on engine displacement?
So in different countries in Europe, in addition to the fuel price being different, actually, the different countries, they subsidize diesel fuel compared to gasoline. So that's part of the, and also they tax the engines with a pretty significant tax in a way that tends to bias it towards getting diesels as well. But how about just the emission standards? So the money definitely makes the Europeans want to use the diesels. I mean, there's still a lot of them buy gasoline cars, so it's maybe 50. It makes it balanced. Whereas in the U.S., there's no way. It'd be way more expensive to get a diesel. But how about for the environmental rules? Anybody know? So environmental rules, the standards are different by a factor of 2 for NOx. Now, a factor of 2 is not that much of a difference. But it turns out that it's very crucial for NOx because it's possible, if you really do a good job with the diesel engine without the emission control system, you can still make the European standard, just barely, if you do it just right. Whereas the US standard, it's impossible. You'd have to put in the urea system to make the NOx standard in the US. So the US standard is just a little bit tighter, but it's right crucial at the moment where it's just impossible. Now, what the European cheaters did was they made their cars meet the legal European standard at the running of the test procedure, but then when the driver got in and started going off the test procedure RPMs, different than the way the test procedure is, then they just got rid of all the controls and said, do whatever you want. And so that way the driver can drive any way they want, get any acceleration they want, even though it took the engine into regimes where the NOx emissions would be much higher. So that was the cheat. The cars were capable to run and meet the NOx standard. And in fact, in the test, they did meet the NOx standard. But then they were set. The problem with that is it makes the power less, the responsiveness less. They have to constrain exactly how they operate. And it's a lot easier if the driver wants to buy an expensive diesel car, they want to be able to go. So they just said, sure, once you're off the test procedure, do whatever the heck you want. And then the consequence was, I don't know if you guys heard about the Paris smog. Do you know about this? I think it was 2 summers ago. There was a few days where there was no wind in Paris, so the pollution just accumulated. And because of the extra NOx emissions, the smog got so bad that many people died in Paris, which is like shocking to Americans. It's like, how can you be in an environmentally minded country, in an area that we think of as having very strict regulations, and then somehow they're just poisoning themselves with their own pollution. And then I would say my view is in China, similar things happening. They actually have very strict standards, very similar to the US or Europe. But if you go to Beijing, you wouldn't know it, right? So something is obviously wrong, that the rules are not really being enforced or something, so that the pollution is worse than you would expect for the amount of emission you should have. Yeah?
For me, though, it's shocking. So I'm European, and for me, it was shocking to come here and see these huge cars.
Yep.
Like enormous.
Yep.
So, do you think that those cars contaminate less than an actual, like, smaller car?
No. No.
I mean, the
No.
ratio is like,
Yeah. So the U.S. standard is the NOx. Yeah, actually, I think it's NOx per mile, right? Does anybody know? I believe. Is it per amount of fuel you burn, or is it per mile you travel? Oh, per kilowatt hour. Okay, so if you have a big vehicle, you make more kilowatt hours, you're allowed to put more emission. So probably, really it's that the ratio of how much NOx you make, probably ratio to CO2 or something like that is really what's being regulated. So the NOx is produced more dilute in the US, but if you have a Chevy Suburban, you're definitely putting out more NOx than you are if you're driving like a Fiat 500. So I mean, this is definitely a problem in this country. And even though we have very, very strict regulations on a lot of things, like in Los Angeles, you'll still get bad smog days, primarily driven by the vehicles, because people are driving big vehicles and a lot of vehicles and a lot of miles. Yeah, whereas actually the miles per car is much more in the US than it is in most other countries too, because people like to drive. Well, you're in a big, comfortable car. You got plenty of room to stretch out. All right. Okay, sorry, we should stop. Let's take a break. Let's get coffee, and then we'll come back and talk about how the different engines want different fuel performance.